Nobel Laureate Adam Rees just made a statement that shook the entire scientific community to its core. The physicist openly declared that the James Webb Space Telescope has found evidence suggesting our understanding of the universe is fundamentally flawed. What Webb discovered in the deepest regions of space isn't just surprising. It's completely rewriting the rules of cosmic evolution. Ancient galaxies like J0107a that formed when the universe was barely 2.7 billion years old display characteristics that should be impossible. In comparison, other Webb discoveries push back to just 400 million years after the Big Bang. These findings are so revolutionary that they force scientists to question whether we've been wrong about everything. But the most disturbing part is what astronomers found hiding in Webb's profound field observations. Among these observations, one galaxy stands out as particularly impossible: J0107a, a colossal barred spiral galaxy existing 11.1 billion years ago when the universe was barely 2.7 billion years old. Represents everything that shouldn't exist according to our current models. This massive structure displays a well-defined spiral pattern with a central bar, remarkably similar to our Milky Way. Yet, it contains over 100 billion solar masses and forms stars 300 times faster than our galaxy. What makes J0107a truly impossible isn't just its size and sophisticated organization. Models say building a mature galaxy takes several hundred million years, yet Webb found J0107a accomplished this in a fraction of that time. The galaxy sports clear bar and spiral arms, structures that simulations predict should take 3 to 5 times longer to develop than the available cosmic time. Instead of the chaotic, irregular blobs astronomers expected to find in the early universe, J0107a appears as organized and mature as galaxies we observe today. The galaxy's stellar mass presents another fundamental contradiction. Reaching 100 billion solar masses requires continuous star formation over extended periods. Yet J0107a achieved this when the universe had existed for only 2.7 billion years. The mathematical requirements for accumulating such mass within the available time frame push beyond what current formation models can accommodate. Even more puzzling, the galaxy maintains this intense star formation rate of 300 times the Milky Way's output, without showing signs of gas depletion or feedback mechanisms that should regulate such extreme activity. J0107a isn't alone in defying expectations. Webb identified other early giants like GNZ11, which had been observed just 400 million years after the Big Bang and appeared unexpectedly bright and actively formed stars. These discoveries represent a pattern of mature, massive galaxies existing far earlier than theoretical models predict. Perhaps most troubling, these early galaxies show no evidence of the merger signatures that should dominate their formation process. Current models predict that galaxies grow primarily through collisions and mergers, processes that leave distinctive tidal streams and disturbed structures. Yet J0107a and similar early galaxies appear remarkably undisturbed, existing in apparent isolation during what should have been the most chaotic period of cosmic evolution. The presence of supermassive black holes in these ancient structures compounds the mystery. These black holes, containing billions of solar masses, require extended periods of matter accretion to reach such sizes. The growth rates necessary to achieve observed masses within the available time frame exceed theoretical maximum limits, suggesting formation mechanisms outside our current understanding. Each new Webb observation reveals additional galaxies that challenge fundamental assumptions about cosmic evolution. The scale of these contradictions suggests that something more profound than individual formation processes might be wrong with our models. The problem isn't just what these galaxies are, but when they manage to exist. The fundamental challenge astronomers now face centers on the universe's rigid timeline constraints. According to current physics, time itself has become the limiting factor that makes Webb's observations impossible. The universe operates on strict schedules that govern when specific processes can occur, and Webb's findings violate every single one of these cosmic timelines. Building a galaxy demands dark matter scaffolding, gas cooling, first-generation stars, and supernova enrichment, all of which Webb sees completed in under 400 million years, defying simulations that need 800 million to 1 billion years. Galaxy formation requires a carefully orchestrated sequence of events unfolding over hundreds of millions of years. Yet, Webb discovered galaxies that completed this multi-stage process within just 400 million years after the Big Bang. During these periods, when impossible galaxies formed, the universe was a hostile environment that should have prevented such rapid development. Temperatures remained extremely high, with radiation constantly heating gas and controlling the cooling necessary for condensation. The cosmic expansion rate was much faster than today, working against gravitational collapse. Dark matter structures still formed their fundamental framework, providing insufficient gravitational anchoring for complex galaxy assembly. Simulations show dark matter halos big enough for these masses shouldn't assemble until at least twice the observed time. The mathematical models governing dark matter physics cannot produce the required infrastructure in the available time frame. Computer simulations consistently demonstrate that achieving the halo masses necessary to support Webb's observed galaxies requires at least 800 million to 1 billion years under optimal conditions. Organized spiral structures in early galaxies push the timeline problem beyond any possible solution. Spiral arms form through density wave propagation, which requires multiple galactic rotations spanning hundreds of millions of years. The mathematical impossibility of achieving observed stellar masses within available timeframes creates an unsolvable equation. Stars form at rates limited by gas collapse and nuclear ignition physics. Even under the most optimistic conditions, producing the stellar populations Webb observes would require star formation rates that exceed theoretical maximums by factors of 10 to 20. Multiple independent research teams across different institutions now report similar timeline violations, confirming that Webb's discoveries represent a systematic breakdown in our cosmological understanding rather than isolated anomalies. This timing crisis forces scientists to question fundamental assumptions about cosmic evolution, dark matter behavior, and the nature of physical processes in the early universe. In every scenario, time is the enemy. Yet Webb's observations ignore the clock. However, the timeline problem represents only one layer of a much deeper crisis emerging from Webb's data. Webb's precise measurements have exposed a fundamental crisis in calculating the universe's expansion rate. The telescope's unprecedented accuracy has revealed growing inconsistencies between different methods of measuring cosmic expansion, creating what astronomers now call the Hubble tension. When scientists use Webb's data to measure distances to remote galaxies, they consistently find systematic discrepancies that cannot be explained as measurement errors. The numbers simply don't match. Traditional measurements using distant supernovae consistently yield expansion rates around 73 kilometers per second per megaparsec. Meanwhile, cosmic microwave background radiation calculations predict a rate of approximately 67 kilometers per second per megaparsec. Webb's measurements, coming in at roughly 72.6 kilometers per second per megaparsec, have deepened this divide rather than resolving it. This 6-unit difference might seem small, but it represents a fundamental breakdown in our understanding of cosmic mechanics. Webb's sharper observations and high redshift galaxy data have reinforced the discrepancy plaguing cosmology for years. The telescope's infrared capabilities allow it to peer deeper into space than ever before, providing distance measurements with unprecedented precision. These measurements consistently confirm the higher expansion rate, making the tension between different measurement methods more pronounced than ever. These measurement discrepancies profoundly affect our understanding of cosmic age and evolution. If the universe expands faster than we calculated, the cosmos is younger than we thought. A younger universe creates even more severe timeline problems for the impossible galaxies Webb discovered. The mathematics becomes increasingly incompatible with observed reality when we factor in a potentially incorrect expansion rate used to calculate the age of everything we see. Nobel laureates are now openly questioning whether dark energy behaves as previously assumed. The standard cosmological model treats dark energy as a constant force driving accelerated expansion throughout cosmic history. However, early-stage speculation among leading scientists suggests that dark energy might not remain constant. Some peer-reviewed studies hint at a weakening dark energy over time, though this remains highly theoretical. The expansion rate varies in ways that could violate our fundamental assumptions about this mysterious force that comprises roughly 70% of the universe. A variable expansion rate creates massive implications for early universe conditions. If expansion rates fluctuated during the first billion years after the Big Bang, it could explain how massive galaxies formed in impossibly short timeframes. Periods of slower expansion would allow more time for gravitational collapse and galaxy assembly. In comparison, periods of faster expansion would stretch distances and affect how we interpret observed structures' age and formation timescales. If our ruler for cosmic time is off, the supposed timeline crisis for these massive young galaxies gets even worse. The expansion crisis compounds every problem with early galaxy formation, pushing us toward conclusions that challenge the very foundations of modern cosmology. These revelations point to two critical breakthroughs that are reshaping astronomy. First, Webb has discovered impossible early giants like J0107a, massive barred spiral galaxies formed when the universe was barely 2.7 billion years old, defying every timeline our models predict. Second, Hubble's constant measurements create an expansion crisis, with different methods yielding incompatible results that suggest our cosmic ruler might be broken. Are our cosmological models fundamentally flawed, or is the universe stranger than we ever imagined? The evidence suggests we're witnessing the birth of entirely new physics that could revolutionize human understanding. Stay tuned as astronomers work to rewrite the cosmic playbook. Comment below. Which Webb discovery shocked you most? J0107a's massive spiral structure or the accelerating expansion puzzle? If you're as fascinated by space as we are, you won't want to miss these other videos. We dive even deeper into the universe's secrets and explore recent discoveries that could revolutionize your understanding of the cosmos. Thank you for joining us on this cosmic adventure. Stay curious and keep looking up.